You've followed enough stories in astronomy to know that most comets behave. They warm up, they brighten, they shed gas and dust, and they follow trajectories we can predict down to the hour. But every once in a while, something crosses into the solar system that forces astronomers to admit a sentence they don't like saying out loud. We have no idea what's going on. 3I Atlas is one of those objects. From the moment it appeared in survey data, something felt off. Not dramatic, not alarming, just off. Astronomers watching the early brightness measurements noticed small deviations from the models, barely enough to raise an eyebrow. But instead of settling into a pattern like every other comet, 3I Atlas kept sliding away from the predictions. Each new observation added more numbers, but fewer answers. And then came the first anomaly that no one could ignore: the color shift. Comets do change color when they approach the sun. That's normal. But 3I Atlas didn't shift once. It shifted multiple times, and not at the distances where the physics says those shifts should happen. One week, it carried a faint green glow, likely from excited carbon-based gases. Later, it appeared much paler, almost white. Then, near mid-inbound, the spectrum pushed toward a warmer yellow, before dipping back into a desaturated green. 3 transitions. 3 different regimes of chemistry. None matching the models. This was the moment the story broke out of the quiet back rooms of observatories and into the wider scientific community. And if you're someone who follows astronomy closely, you know that scientists don't panic when they see something strange. But they do pay attention. Very close attention. So telescopes across the world were pointed toward this object. Telescopes that have tracked comets for decades. Telescopes that know the signatures of water, carbon monoxide, carbon dioxide, and dust better than any human eye ever could. And they all kept coming back with the same quiet message. This one is not following the rules. Its coma should have grown gradually. Instead, early images suggested it expanded faster than expected, so fast that its size estimates didn't match its brightness. Its jet activity should have lined up with solar heating. Instead, the geometry looked asymmetric and unstable. The ratios of gas in its spectrum didn't resemble the structure of typical comets in our solar system. And then came the data from the James Webb Space Telescope. If any instrument could settle the argument, it was Webb. Its infrared spectrograph can pull chemistry out of a faint smear of light like no observatory before it. The expectation was that Webb would clean up the confusion. It didn't. Webb found that 3I Atlas was dominated by carbon dioxide, far more than expected. In fact, CO2 seemed to outweigh water by factors no one had modeled for an interstellar comet. It wasn't impossible, but it pushed the conversation into uncomfortable territory. Either this comet formed in a radically different environment than comets here, or something had altered its surface over billions of years in deep interstellar space. Both possibilities were interesting. Neither solved the prediction problem. And then came the moment that should have clarified everything. The Mars pass-by. For a brief window, 3I Atlas passed within 30 million kilometers of the red planet, a geometry so rare that mission teams moved the high-rise camera on the Mars Reconnaissance Orbiter into position. HiRISE sees the solar system from an angle Earth-based telescopes never get. At 30 kilometers per pixel, these images were expected to be the highest value dataset collected before the comet reached perihelion. but the images didn't appear. A week passed, then 2, then 3. Astronomers who had already prepared follow-up observation programs began running out of time. Discussions spread across private research forums. Even the public noticed. Reporters asked questions. A U.S. representative reached out to NASA directly, asking for disclosure. And while people argued, 3I Atlas just kept moving, kept shedding mass, kept changing, but not in a way anyone could model confidently. Not in a way anyone could simply plug into standard comet physics. This is where you enter the story tonight. Because the more the world tracked this object, the less predictable it became. Every piece of new data contradicted the last. Every explanation solved a small part of the puzzle, but broke another. And for astronomers, that's not a crisis. That's the start of discovery. You're listening to this because you're the kind of person who pays attention to the sky, not for drama, but for the quiet satisfaction of knowing how the universe behaves. You enjoy the patterns, the precision, the cold elegance of celestial mechanics. That's exactly why 3I Atlas deserves your attention. This visitor from another star system isn't dangerous. It isn't threatening Earth. And it isn't sending signals or performing maneuvers that hint at artificial intent. But it is doing something rare. It's challenging the limits of our predictions. And that's the real value of this story. Not fear, not speculation, but the reminder that even in 2025, with our best instruments and our brightest minds, the universe can still surprise us. It can still behave in ways that force us to rethink what we thought we understood. Tonight, you'll follow that surprise from the first detection to the moment the models broke, through the Mars flyby, the political noise, the chemistry debates, and the attempts to reconstruct what this object really is. Because if there's one truth 3I Atlas has made clear, it's this. The deeper we look into the behavior of something born under a different star, the more it reminds us how little we can predict. You remember where this story started, with a comet that refused to behave. But to understand how the predictions fell apart, you have to go back to the very first night astronomers realized something unusual had slipped into the solar system. It was July 1st, 2025. At the Atlas Survey Facility in Chile, the automated system picked up a faint streak of light cutting across sequential frames. Nothing dramatic. Nothing that suggested this would turn into one of the most puzzling interstellar objects ever recorded. Just a narrow line where there hadn't been one before. The kind of detection astronomers see hundreds of times a year. But as soon as analysts began running orbital solutions, the first alarm bell rang quietly but persistently. The numbers didn't fit a bound object. The early calculations showed an eccentricity around 1.7, far above the threshold for a closed orbit. Hyperbolic. Only one thing gives you a hyperbolic signature like that. An object that came from outside the solar system. Interstellar. Again. And with that single detail, astronomers shifted their expectations. Interstellar objects are rare, but no longer shocking. Oumuamua came first, then Borisov. And now, apparently, a third, 3I Atlas. Each one brought different chemistry, structure, and behavior, but they all still played within the general boundaries of comet physics. The thinking was simple. Another visitor, another chance to learn, another data point. This time, everything would be clearer. But within hours of analysis, the certainty began to dissolve. When astronomers examined the early brightness data, something stood out immediately. The comet was already more active than an interstellar object should have been at that distance. Too active. The coma, its outer cloud of escaping gas, was swelling faster than expected, and at a distance where solar heating should have been gentle. It wasn't impossible, just unusual. The kind of detail you mark in a notebook with a single line under it. Not a red flag, just a curiosity. Still, the anomaly didn't fade. Follow-up observations a few nights later confirmed the trend. The coma was expanding rapidly, and the flux measurements didn't align with any model the teams were using. A visitor from another star system is supposed to wake up slowly, gradually, as the sun's heat begins to unlock ancient ices. But this thing was waking up early, like someone turning on the lights in a room moments before they were expected to enter. The chemistry made it stranger. Normally, when a comet begins to activate, water is the star of the show. Water vapor drives the activity. Water generates the coma. Water sets the early behavior. But 3I Atlas wasn't listening. Water was barely detectable. The signatures were faint, so faint some teams couldn't measure them at all. Meanwhile, carbon dioxide was roaring. CO2 dominated the spectrum from the start, far more than any comparable object in the solar system. It was as if the comet had skipped the water stage entirely and jumped straight to a mode of outgassing that normally appears much later. CO2, this strong, this early, at this distance. There's no standard explanation for that combination. You can say, different formation environment, and that's true enough. But it doesn't fix the prediction problem. Something was happening that didn't map onto known behavior. And then the brightness problem emerged. Brightness in a comet is supposed to correlate with size and activity. If you know one, you can usually estimate the others. But 3I Atlas refused to give consistent numbers. Size estimates based on reflectivity suggested one thing. Size estimates based on gas production suggested another. And the coma intensity suggested something else entirely. Everything about this object seemed to disagree with itself. This is where the confusion moved from interesting anomaly to this doesn't make sense. To make matters even more complicated, astronomers couldn't detect a reliable rotation period. Most comets flicker as they spin, tiny rises and dips in brightness that reveal how the nucleus turns in space. But 3I Atlas didn't flicker. Not in the early light curves, not in the second round of observations, not even in the deeper analysis from larger telescopes. It just sat there, glowing steadily, with no sign of the usual rhythm. No rotation signature means no clear way to model how jets form, or how material escapes, or what parts of the nucleus are heating up. Without a rotation period, you lose a whole dimension of predictive power. When you put all of this together, the early activity, the oversized coma, the unusual chemistry, the brightness mismatch, the missing rotation, the message becomes unavoidable. From the very first week, the data resisted prediction. The comet was communicating something through its behavior, and what it was saying was simple. The rules written for solar system comets do not apply here. You could sense the shift in tone across scientific discussions. No one was sounding alarms. No one was claiming danger. But the level of attention tightened. The vocabulary changed. Caution replaced confidence. The early papers used phrases like unexpected, poorly constrained, unusual composition, and requires further observation. And in a quiet interview, when asked what made this object so different, University of Iowa astronomer Ken Gay summed it up in one sentence that caught on quickly. Differences are expected, but this one is unusually different. For a scientist, that's as close as you get to saying, "This is not what we thought we were dealing with." By now, you can feel the pattern forming. This is the foundation of the predictive breakdown. Not one big mystery, but a stack of smaller ones, each one nudging the comet further away from the models built to explain it. And the strangest part is that this wasn't the dramatic phase of the story. This was the beginning, the moment when the first cracks appeared in the certainty surrounding the object. No loud surprises, just a steady, accumulating sense that something wasn't aligning. And then, the closer we looked, the stranger it became. When astronomers confirmed that 3I Atlas came from beyond the solar system, they already had two benchmarks in mind. Two previous visitors, two case studies that hinted at what interstellar could look like. You might remember them. 1 Oumuamua in 2017 and 2I Borisov in 2019. Together, they formed the beginning of a pattern, if you could call it that. Oumuamua was the quiet one. No coma, no tail, no detectable outgassing, and an odd shape that bent ideas about what a natural fragment should look like. It behaved more like a reflective shard than a comet. Its acceleration confused everyone. Its chemistry remained largely invisible. Borisov, on the other hand, was almost comforting in its normality. It looked like a typical comet, acted like one, and shed gas and dust in a way that made sense. Where Oumuamua broke the rules, Borisov restored them. So when 3I Atlas appeared, the unspoken hope was simple. Maybe this one will help us connect the dots. A third visitor could show whether interstellar objects carry a signature pattern or if each is an isolated exception. But the more the telescope saw, the more that hope slipped away. Hubble was the first major observatory to lock onto it. From Earth's vantage point, the angle wasn't ideal. Our planet lined up almost edge-on with the sun, giving a narrow perspective. But even from that alignment, Hubble's long exposures carved out a shape that made astronomers pause. The coma wasn't round. It wasn't symmetrical. It stretched and tapered like a faint teardrop, a drifting drop of light shedding material unevenly into space. A teardrop coma isn't unheard of, but the degree of asymmetry, the way the light seemed to pool more strongly on one side, raised questions. Was this due to a surface region heating unevenly, a jet firing off axis, or was the entire nucleus shaped in a way that directed the outgassing to one side? Without a rotation signature, there was no easy answer. It was a picture that asked more than it answered, and that image wasn't the only surprise. Additional analyses revealed the scale of the coma, an immense envelope of gas stretching nearly 348,000 kilometers across. For reference, the average distance between Earth and the Moon is about 384,000 kilometers. This meant that the coma of 3I Atlas was almost lunar in size, an entire world-sized cloud of material expanding around a nucleus barely a few kilometers wide. This kind of scale doesn't happen often. It requires intense activity, driven by a source that is either exceptionally volatile or exceptionally unusual. That question, unusual how, found its next clue through the James Webb Space Telescope. JWST turned its infrared spectrograph toward the comet, and if any instrument was going to clarify the chemistry, it was Webb. What it saw didn't match standard comet behavior, not even close. The ratio of carbon dioxide to water was staggering. CO2 wasn't just dominant, it outweighed water by nearly a factor of 8, a chemical imbalance that pushed the object into a category all its own. In comets from our solar system, water is the foundation. It's the first to activate, the main driver of outgassing, and the core ingredient of cometary behavior. Carbon dioxide appears, yes, but it doesn't usually lead the show, especially at this magnitude. So what does CO2 dominance mean? An object could form in a region far colder than where most comets originate, or it could have traveled through harsh environments, its outer layers transformed by cosmic rays into new chemical structures. That would leave it wrapped in a processed shell, unlike anything seen locally. Clean CO2, unshielded water, and a surface composition shaped by billions of years of wandering. CO2 this pure is like seeing a fingerprint that no one in the solar system shares. But Webb's results only deepened the puzzle. If the comet was dominated by carbon dioxide, then the tail and coma should reflect that. Yet the dust tail was strangely faint, barely visible against the background stars. A powerful gas-driven object should have carried a stronger dust signature, but here the models broke again. Too much gas, too little dust, a mismatch between the theory and the light. And still, through all of this, the rotation problem remained unsolved. Telescopes around the world checked for flickers in brightness, little rises and dips that would signal spin. Nothing showed, not in the early days, not in the later ones, not in the longest exposure, highest sensitivity data sets. It was a steady glow, almost eerily consistent for an object shedding material at such a rate. It raised a question that astronomers don't like having to ask. What if the rotation period is too slow or too unusual for us to detect? A nucleus spinning irregularly or barely at all would break another set of predictive tools. Without rotation, you can't easily map where jets might appear, how mass loss evolves, or how sunlight distributes across the surface. Without rotation, you lose another language the comet could have used to explain itself. So here's the picture that started to form. Slowly, reluctantly, and with more confusion than clarity. 3I Atlas behaved partly like a comet. It built a coma. It shed gas. It responded to sunlight, but its chemistry resembled something foreign. Its brightness didn't match its size. Its dust didn't align with its gas output, and its rotation remained invisible. It was both familiar and unfamiliar, predictable in theory, unpredictable in reality. A visitor shaped by physics you recognize, but tuned in a way that felt alien, not because it was technological, but because it was born under conditions you've never seen directly. A fragment of a different star's story, carrying a composition that made sense only on worlds you've never visited. This is where the sense of wonder mixes with confusion. The sweet spot where astronomy becomes not just science, but discovery. And if you're the kind of person who listens to stories about the universe at night, you know that discovery rarely begins with clarity. It usually begins with contradictions, with details that almost fit but not quite, with an object that looks like it should behave but doesn't, with a drop of light stretching into a shape you can't model. Nature is more clever than our expectations, Avi Loeb once said. And objects like this prove him right every time. But the universe saved the strangest perspective for Mars. You've seen comets from Earth your entire life, at least in photographs. Bright arcs, long tails, glowing comae, always from the same general angle, always filtered through the atmosphere of our own planet. But every so often, the solar system lines up in a way that gives you a vantage point no telescope on Earth can offer. And for 3I Atlas, that moment came when it drifted into a perfect alignment with Mars. It didn't dive close to the planet. It didn't skim its atmosphere or pass near any Martian moons. Instead, it slid by at a distance of 29 to 30 million kilometers, far, but close enough for orbiting instruments to capture something invaluable. Distance isn't everything in astronomy. Geometry matters more. And the geometry that night was extraordinary. The Mars Reconnaissance Orbiter, circling the red planet since 2006, carries one of the sharpest cameras ever sent beyond Earth. HiRISE. If Hubble gives humanity a pair of excellent eyes, HiRISE gives us the ability to see with a level of crispness that feels almost impossible for a camera millions of kilometers away from home. Its resolution pushes down to about 30 kilometers per pixel when aimed at a target as distant as the path of 3I Atlas. That meant for this object, HiRISE had roughly 3 times the spatial clarity of Hubble's best attempt. But the advantage wasn't only sharpness. It was angle. From Earth, you look at 3I Atlas almost along the line between the Sun and the comet, a perspective that flattens out the cloud of gas around it. That makes it hard to figure out where exactly the mass is escaping from. Almost everything is backlit. Details overlap. The shape of the coma blends into one glowing field. But from Mars, the comet was off to the side. A sideways view. A view where incoming sunlight scattered across the coma instead of blasting through it. A view no Earth-based telescope could ever achieve. In comet science, a sideways perspective is priceless. It lets you decode the geometry of the mass loss, identify which regions of the nucleus are shedding material, estimate how fast jets are firing, and see how dust and gas separate as they drift through space. For an interstellar object behaving as strangely as 3I Atlas, this wasn't just helpful, it was critical. The plan was straightforward. Capture HiRISE images on October 2nd and 3rd, 2025, just before the comet's approach toward perihelion. These images would give scientists the best chance to understand what was happening before solar heating peaked. They would anchor models. They would resolve questions the Hubble and Webb data sets had opened. They would let astronomers compare the object's early strange behavior with its mid-inbound physics. Everyone expected the images to be released quickly. HiRISE data has appeared publicly within days for years. The pipeline is efficient, the mission team is experienced, and comet observations always draw scientific interest. The community waited, and waited, and waited. A week passed, nothing. 2 weeks passed, nothing. 3 weeks passed, still nothing. For astronomers tracking an interstellar visitor that would never return, timing mattered. The comet was continuing to heat, continuing to lose mass, continuing to shift in brightness and chemistry. Every day that passed without the data meant models had to be revised without the most important puzzle piece. This wasn't a mere delay. It was a hole in the story at the exact moment when clarity was needed most. And then came the 4th week. Silence. That was the moment people started asking questions. In private emails, in scientific Slack channels, in symposium hallways, and then in public. Why was NASA holding the images? Why now? And why this object? Why lock the highest value dataset of the entire approach? Astronomers tried to guess at the answer, but each guess felt worse than the last. Some thought there might have been an issue with the data pipeline. Others wondered whether the images hadn't come out well enough to release. But those explanations didn't last long. HiRISE has handled harder shots. It has released flawed images before. Nothing about this target justified 4 weeks of silence. Instead of clarity, the community got an entirely different announcement. The U.S. government shutdown on October 1st had paused certain federal operations. According to NASA, the delay was administrative. A paperwork traffic jam, a system freeze. Maybe that was true. Maybe it wasn't the whole story. But even if bureaucracy was the reason, it didn't erase the problem. You can't delay time-sensitive science when the object you're studying is racing toward the sun and about to transform again. And that's when the tone shifted from curiosity to concern. Scientists don't like mysteries created by human intervention. It's one thing when the universe surprises you. It's another when an agency sits on crucial data during the most dynamic phase of a comet's journey. The tension wasn't fear. It wasn't hype. It was frustration. It was the quiet, concentrated frustration of experts who knew that every missing hour made the next step harder. Avi Loeb said it cleanly during an interview when someone asked about the delay. His answer traveled quickly through research circles. Data delays hurt science more than any mystery in the sky. What made the situation more uneasy was this simple fact. Earth had no angle to see what Mars saw. From our planet, we were effectively blind to the sideways view. For those 4 weeks, it wasn't an exaggeration to say that humanity had no idea what the comet looked like from the only vantage point capable of revealing its true shape. We saw nothing, but Mars did. And the sense of being locked out of that view, of missing a once-in-a-lifetime geometry, added a new layer to the story. Not a sensational one, not a dramatic one, but a human one. The object was doing something unusual, and the only instrument positioned to decode that behavior was silent. Meanwhile, the comet just kept moving, past Mars, toward the sun, toward a brightness peak no one could fully model. There was no stopping it, no repeating the observation, no second chance baked into orbital mechanics. The data was either released in time, or it became nothing more than a retrospective curiosity. And for an interstellar object that might not resemble anything we'll see again for decades, that was a difficult thought to swallow. You could feel the arc of the story bending. The mystery of the comet had now collided with the silence of bureaucracy. And that collision pushed the entire narrative into a new phase, one where the object itself was no longer the only unknown. And then, confusion turned into controversy. When the silence around the Mars images stretched into its 4th week, curiosity turned into public attention. It began quietly, as most scientific stories do, with small discussions on astronomy forums, a few speculative tweets, and a handful of researchers mentioning the delay during live streams. But everything changed the moment a headline appeared in the New York Post. The article was direct. Representative Anna Paulina Luna had formally requested that NASA release the unreleased high-rise images of 3I Atlas. For most people, political involvement in astronomy is unusual. For astronomers, it is something they prefer to avoid entirely. But the story was simple enough for the public to follow. A rare interstellar object had drifted past Mars. NASA had photographed it. Weeks had passed with no data release. And now, a member of Congress wanted answers. In online discussions, the detail that caught fire wasn't the orbital geometry or the resolution advantage of high-rise. It was the color shift. Users shared side-by-side telescope images. They circled bright patches and tinted regions. They speculated about chemistry and physics, but also about meanings far beyond science. Words like artificial and engineered appeared in comment sections, often without evidence, often with more imagination than restraint. It didn't help that the color shifts genuinely were strange. Green to white to yellow and back again. Most comets don't cycle through that sequence, and certainly not at those distances. For people who follow astronomy casually, it felt like a signal. For experts, it was a reminder that chemistry in interstellar objects often defies expectations. But for the general public, the combination of delay and mystery was too tempting to ignore. NASA eventually explained the situation. The data couldn't be processed or released because of the federal shutdown on October 1st. They insisted it was a procedural bottleneck, not a scientific one. Under normal circumstances, that might have settled things. But this wasn't a normal circumstance. This was an interstellar object. The third one ever detected. The only one we had seen from the vantage point of Mars. Shutting down routine operations is one thing. Shutting down a once-in-a-lifetime data set is another. The shutdown explanation spread, but it didn't calm the conversation. If anything, it made the frustration sharper. The idea that politics, not physics, was slowing down one of the most valuable data sets of the year left a sour taste. People weren't angry. They were disappointed. Science had been pushed aside by paperwork. Avi Loeb, who had spoken publicly about the delay during interviews, put it in a way that resonated with both scientists and the general public. The delay is probably not a sign of extraterrestrial intelligence, but of terrestrial stupidity. It was blunt. It was honest. And it captured exactly how the situation felt. The problem wasn't that something was being hidden. The problem was that a bureaucratic freeze had disrupted a global scientific effort at the exact moment it needed clarity. Still, the public conversation evolved into two camps. One group argued this was simply a case of bad timing. A shutdown interrupts agencies. The system froze. Nothing more. They believed the images would be released when normal operations resumed. They trusted the process. The other group wasn't convinced. They pointed to the unusual brightness behavior, the powerful CO2 emissions, the color changes, and the strange shape of the coma. They combined the silence with the anomalies and asked, "What is NASA not showing us?" Their theories ranged from harmless speculation to far-reaching interpretations. In truth, neither side knew anything yet. No one outside NASA had seen the images. No researcher had the geometry needed to confirm the mass loss structures. And no one could say whether the comet was natural or something stranger. The discussion spread across news segments, online communities, and podcasts. Some hosts joked, Others speculated seriously. A few leaned into dramatics, but most listeners simply wanted the same thing astronomers wanted: the raw data, the actual images, the truth that only HiRISE could provide. Through all the commentary, one question kept resurfacing, quietly but persistently. What do the images contain? And that question, more than anything else, pushed the story beyond science and into the wider world. It wasn't sensational. It wasn't fearful. It was the natural curiosity of people who follow the sky. People who know that sometimes the universe puts something in front of us that we don't understand yet, and all we can do is look closer. Representative Luna's letter became the focal point. It wasn't confrontational. It wasn't accusatory. It was straightforward, a request for transparency, a reminder that scientific data belongs to everyone, not just agencies, a nudge to move the process along when the world was watching. And whether you follow science through news articles, telescopes, or late-night videos like this one, you could feel the shift. The comet was no longer just a distant object moving through space. It had become a point of public interest, a meeting place where astronomy, government procedure, and global curiosity crossed paths. But the truth is simple. The controversy wasn't the center of the mystery. It was just the shadow cast by something deeper, the real puzzle, the one that kept astronomers awake at night and filled observation proposals worldwide, wasn't political at all. It was scientific. The comet's behavior didn't match the models. Its chemistry didn't match known patterns. Its structure didn't match the predictions. The silence from NASA only sharpened the question that everyone, from professional astronomers to casual skywatchers, was already asking. If this is how strange the early data was, what were the Mars images going to show? But behind the controversy lay a deeper scientific puzzle. Once the controversy began to spread, astronomers did what they always do when faced with an object that refuses to obey the rules. They went back to first principles. They asked what a natural explanation might look like. They gathered the chemistry, the light curves, the shape of the coma, the faint tail, the rotation data, or lack of it, and tried to make all the pieces line up. That is the essence of science. Not jumping to conclusions, but testing the familiar before entertaining the extraordinary. But with 3i Atlas, each familiar explanation came with an asterisk, a footnote, a quiet caveat, something that almost fit, but not quite. The first possibility was perhaps the most straightforward: formation beyond the snowline. In astronomy, the snowline is the distance from a star where temperatures fall low enough for volatile ices, like carbon dioxide, to solidify. In our solar system, that line sits far beyond Mars, somewhere in the colder outer regions where comets typically form. If 3i Atlas formed around a colder, dimmer star, its CO2-rich shell might simply reflect the chemistry of its birthplace. That explanation checked a few boxes. It could account for the dominance of carbon dioxide in the early spectra. It could explain why the comet began outgassing CO2 instead of water. It might even offer insight into the unusual activity distance. But the problem came quickly. If the object was formed entirely outside a warm zone, why was water present at all? And if it did hold water, why was that water so deeply suppressed that even Webb struggled to measure it? A pure snowline origin worked on paper, but it didn't explain the chemical imbalance. It solved the CO2 question, but broke the water question. So scientists turned to a second explanation: a cosmic ray processed crust. Out in interstellar space, far away from the protection of a star's magnetic field or solar wind, comets drift through a sea of high-energy cosmic rays. These charged particles strike their surfaces for millions, even billions of years, rearranging molecules, breaking bonds, and creating new chemical layers. It's a form of slow, steady sculpting, radiation chemistry acting on ancient ice. Under this model, water near the surface could have been split into other compounds, while carbon monoxide and carbon dioxide built up over time. A thick, altered crust might hide the original ingredients underneath. When the comet entered the solar system, sunlight would heat the processed outer layers first, causing CO2 to dominate the early outgassing. It was a compelling idea, elegant. It matched the dominance of carbon dioxide and the faintness of water signatures, but it didn't explain everything. If cosmic rays transform the outer layers, then heating should reveal deeper layers over time, layers richer in water. Yet as Atlas moved closer to the sun, water signatures didn't rise as strongly as expected. The crust explanation answered one question, but weakened another. So astronomers considered the possibility that the water was simply buried much deeper than usual. In some comets, thick layers of refractory material, a mixture of dust, rocky grains, and processed ice, sit atop cleaner, more volatile ices. If 3I Atlas had a particularly dense shell, its water might be locked beneath it, sealed off until stronger solar heating occurred later in its journey. This deep water hypothesis gained traction. It fit the idea of a dry exterior with a volatile interior. It explained why the comet could erupt in CO2 while remaining quiet in water. It hinted at a structure not unlike some Kuiper Belt objects. But again, the issue came down to timing. At the distances where Atlas was already active, the sun's heat should have penetrated deeper than the data suggested. A sealed interior didn't remain sealed this far inbound. The timing didn't fit. The model worked in isolation, but not in the real sequence of observations. So researchers expanded the possibilities further. A few groups proposed that 3I Atlas might not be a single object at all, but a loose fragment swarm, a cluster of pieces held close together by low mutual gravity. If the object had fractured long ago, each fragment might outgas differently, creating a combined signal that looked inconsistent. That could explain the asymmetric coma, the faint dust production, and the inconsistent brightness measurements. But the fragment swarm model had problems of its own. A cluster should show signs of irregular brightness as pieces occlude one another or drift slightly apart. It should also produce a more chaotic tail. Neither effect appeared in the data. A swarm could account for the inconsistencies, but it didn't match the stability. Another explanation revolved around the geometry of the outgassing. If jets were firing from unusual angles, pointed away from the sun, or bursting from deep cracks, the coma could grow into an odd teardrop shape. This could even influence the comet's trajectory. But that idea broke down when the direction of the force didn't match the direction of the observed asymmetry. The jets, if present, seemed misaligned with the structure of the coma. That brought astronomers to a final natural explanation: the trajectory itself. Comets often receive small pushes from outgassing that slightly alter their paths. But the pushes Atlas experienced didn't line up with the expected direction based on the coma's structure. That meant either the coma wasn't telling the full story, or the models were missing an ingredient. A natural ingredient, yes, but an ingredient that didn't fit the standard set. One by one, each natural hypothesis solved a piece of the puzzle only to break another. It was like trying to fit a key into a lock that turned halfway and then jammed. The explanations weren't wrong in principle. They were wrong in combination. Every answer became another question. You can feel why astronomers were cautious. The object wasn't behaving impossibly. Nothing about it violated physics, but the familiar tools, the models, the ratios, the temperature curves, the chemical expectations weren't working. They clashed with one another in small but persistent ways. This is where the story becomes interesting, not because of drama, but because of how science works. You test one theory, it breaks. You try another. It breaks in a different way. And the more you test, the more you discover the limitations of what you thought you understood. Carl Sagan summarized this kind of moment perfectly. Science begins where predictions fail. And for 3i Atlas, prediction had been failing from the beginning. So you're left with the natural explanations that almost fit but never quite land. A snowline chemistry that seemed logical until the water signature fell apart. A cosmic ray crust that made sense until the deeper layers stayed quiet. A sealed interior that didn't unseal. A fragment swarm that stayed too stable. Outgassing geometry that didn't match the force. A trajectory shift that didn't match the light. Each model worked only when you ignored half the data. And when you're dealing with an interstellar visitor, something shaped by environments you've never seen, carrying chemistry forged around a different star, that is both frustrating and fascinating. It makes you ask the question that everyone following the story eventually asked. If the natural explanations don't quite work, then what exactly are we looking at? But some wondered, what if the predictions fail because the object is not natural? Whenever a cosmic object behaves strangely, the same question eventually finds its way into the conversation. It doesn't matter whether you're a researcher, an amateur astronomer, or someone who watches the night sky through documentaries. At some point, when the models fail and the data refuses to line up, the mind opens a forbidden door. What if this isn't natural? 3i Atlas reached that point, not because anyone wanted it to, but because the stack of inconsistencies grew tall enough that the question became unavoidable. To understand how the debate formed, you have to go back to the first interstellar visitor we ever detected, 1I, Oumuamua. Before Oumuamua, interstellar comets existed only in theory. We knew objects from other star systems should pass through ours. We just didn't have the instruments to catch them. Then in 2017, a cigar-shaped object slipped past the sun at extraordinary speed, with no visible tail and no gas emissions. It looked nothing like anything we had cataloged. And then came the part that shook things loose, the acceleration. Oumuamua sped up slightly as it left the solar system, just enough to notice, too little to explain. It wasn't following a purely gravitational path. When astronomers tried to model the acceleration as outgassing, the numbers didn't match. There was no detectable gas, no coma, no obvious jets, yet the acceleration was real. Some scientists argued that outgassing was happening, but in gases too faint or transparent to detect. Others argued that the shape of the object made its motion unpredictable. And a few, like Avi Loeb, suggested a possibility the scientific community rarely says out loud. Maybe the object wasn't entirely natural. Not because it looked alien. Not because it behaved like a spacecraft, but because when nature removes every obvious mechanism except for the ones we don't understand yet, you have to consider everything that remains. If Oumuamua taught the world anything, it was this. When data is limited, theories multiply. Fast forward to 3I Atlas. Unlike Oumuamua, this visitor wasn't silent. It was active. It had a coma. It shed gas. It behaved like a comet, at least at first glance. But the deeper astronomers looked, the more the comet broke the simple framework of natural object from another star. The first hint came from its chemistry. A shell dominated by CO2, unusually clean, unusually strong, with water suppressed far below typical levels. Comets in our solar system generally carry mixed ices. The ratios vary, but they rarely skew this hard in one direction. A clean CO2 shell is possible, yes, but it makes the comet stand out like a different species. Then came the activity patterns. Atlas woke up early, outgassing at distances where sunlight shouldn't have penetrated deeply enough to unlock such strong reactions. Its coma expanded faster than expected. The dust signature was faint, almost shy, contradicting the strength of the gas. Its brightness didn't match its estimated size. And lacking a detectable rotation period, astronomers had no way to judge how its jets might shape its movement. With all these inconsistencies, it didn't take long for the alien probe question to surface online. Most scientists ignored it. Some dismissed it outright. But others, remembering the debates around Oumuamua, acknowledged that the question didn't come from fantasy. It came from frustration. When natural explanations break down one by one, curiosity fills the gap. Still, the people who investigate these things professionally take a very different tone than social media. The first voice to weigh in publicly was Ken Gay, the astronomy professor from the University of Iowa. His approach was patient, measured, and grounded in decades of comet research. He explained that outgassing can mimic propulsion. If gas vents from one side of a comet more than the other, the escaping material pushes the nucleus in the opposite direction. This can create subtle accelerations that look unnatural. But they aren't. They're physics. Simple physics acting on ancient ice. The difficulty, he said, is that the behavior doesn't always look simple. If the jets are faint, or the materials are unusual, or the chemical ratios are extreme, as they often are in interstellar objects, the result can resemble a maneuver. But a resemblance is not proof. And he reminded audiences of something important. Interstellar objects form around stars that are nothing like the sun. What looks engineered might simply be foreign. Avi Loeb, for his part, has always argued for a broader view of possibilities. Not because he believes every strange object is artificial, but because he believes every strange object deserves to be evaluated on evidence alone. He has said many times that nature can be surprising enough to imitate design. Or as he put it in one interview, it might look engineered, not because someone built it, but because nature can look engineered. This statement captures the middle ground perfectly. Comets can act in ways that resemble intention without being intentional. They can exhibit symmetry, smooth surfaces, sharp edges, and efficient physics, just because that's how the universe works. Still, Loeb also encourages investigating all hypotheses, including artificial ones, as long as the approach is scientific. His position isn't that 3I Atlas must be an alien probe. His position is that dismissing the question outright would be unscientific, which brings the focus back to the object itself. What do we actually know? We know 3I Atlas outgassed heavily. That's natural. We know its chemistry is dominated by CO2. Unusual, but still natural. We know its coma shape is odd. Its dust content is low. Its rotation, mysterious. But nothing in its behavior requires non-natural explanations. Nothing suggests it's transmitting, maneuvering, or responding to anything external. Nothing resembles propulsion, communication, or control. Everything it does can be explained by physics, just not cleanly. The alien probe hypothesis, in the end, falls into a familiar pattern. It is exciting, possible in theory, but unsupported by evidence. And that's the key difference. Astronomers don't ask whether something is possible. They ask whether something is necessary. With 3I Atlas, the answer is clear. The artificial explanation isn't necessary. Natural processes, exotic, messy, and poorly understood, but natural, are sufficient to explain everything we've observed, even if they require us to stretch our understanding. The real intrigue doesn't come from imagining the object as a device. It comes from understanding how a natural visitor from another star system can challenge our assumptions this deeply. It comes from the awareness that comets formed under alien suns can behave in ways that don't match the templates built from comets born under ours. It comes from the reminder that the universe has had billions of years to experiment with chemistry and physics we've barely begun to explore. And so, the debate settles into a quiet equilibrium. The artificial explanation remains a hypothesis of last resort, a mental note, not a conclusion, a placeholder, not a theory, something to keep on the shelf in case future data demands it. But it doesn't demand it. Not here. Not yet. For now, the weight of evidence still rests comfortably on the side of nature. Yet even if it was natural, it still refused to behave naturally. By the time astronomers moved past the artificial object debate, one truth had already settled in. Even if 3I Atlas was entirely natural, and the weight of evidence suggested it was, its behavior still cut straight through the predictions that were supposed to guide our understanding. Every hour of new data revealed another place where the models bent, cracked, or simply broke apart. If you want to understand why forecasts failed, you have to examine the specific tools astronomers depend on when tracking comets. These tools usually work. They've been refined over decades. They've predicted the behavior of hundreds of objects with incredible accuracy. But each tool depends on assumptions that 3Psi Atlas simply didn't follow. The first and most important assumption is rotation. When comets rotate, they reveal themselves. A rotating nucleus produces light curves that rise and fall as different regions turn toward the sun. These subtle fluctuations, sometimes only a few percent, tell astronomers where jets might be located, which parts of the surface heat first, and how the shape of the nucleus might look. But with 3I Atlas, There was nothing. No flicker, no pattern, no periodic signature. Long exposures produce steady brightness. Short exposures produce steady brightness. Multi-night campaigns produce the same steady glow. This absence wasn't comforting. A missing rotation period means you lose the compass needle of comet modeling. Without knowing how the object spins, you can't predict how different parts of the surface will respond to sunlight. You can't chart the evolution of jets. You can't forecast brightness. You can't understand how the object will accelerate through space. It's not that 3i Atlas wasn't rotating. It almost certainly was. But the rotation was either too slow, too chaotic, or too masked by gas emissions for any telescope to detect. And when the rotation vanishes from the data, the predictions follow. Then came the issue of surface composition. Comets in our solar system have surfaces that behave somewhat predictably. Some regions are dusty. Some are icy. Some are fractured or hardened. But the overall behavior is consistent enough that models can take it into account. One region ignites first. Another heats slowly. The patterns follow predictable curves. 3i Atlas didn't. The surface, or whatever was happening just beneath it, appeared irregular in a way that defied easy explanation. Certain regions outgassed CO2 intensely, while others remained quiet far longer than expected. The imbalance wasn't random, but it wasn't stable either. It shifted, evolved, reacted. A comet with a non-uniform surface is expected. A comet with a surface this inconsistent is not. This is where thermal lag should have helped clarify the story. Thermal lag describes the delay between when sunlight hits a surface and when that surface begins releasing gas. Think of it like warming up ice on a winter morning. It doesn't melt instantly. It takes time. This lag allows researchers to predict when and how a comet will brighten as it moves closer to the sun. But here again, 3i Atlas refused to cooperate. The timing of its outgassing didn't match any model. Some jets seemed to activate too early, others too late. Some faded unexpectedly, while others pulsed irregularly. Thermal lag depends on the depth and conductivity of material, and whatever material was hiding beneath the surface of Atlas didn't respond to heat in any predictable way. This alone would make forecasting nearly impossible. But the next issue made it worse. The jets, primarily CO2 jets, were unstable. In a typical comet, jets behave like predictable geysers. They burst, fade, restart, and expand along lines that scientists can model. But jets dominated by carbon dioxide behave differently. CO2 sublimates at lower temperatures. It activates farther from the sun. Its pressure curves are steeper. And in an interstellar object, where CO2 ratios were already extreme, the jets didn't follow the traditional cadence. They triggered irregularly, produced asymmetrical forces, and created coma structures that shifted shape from day to day. When jets refuse to provide consistent thrust, the orbit becomes harder to forecast. And that's where the dust-to-gas ratio comes in. In most comets, dust acts like a tracer. It reveals what the gas is doing. It outlines the shape of the jets. It creates visible tails that reflect sunlight in ways that are easy to measure. But 3i Atlas barely produced dust. The dust tail existed, faint, thread-like, quiet, but it didn't carry the expected complexity. The gas was shouting. The dust was whispering. This disconnect removed yet another tool astronomers rely on. Without dust, you lose another window into the object's behavior. Without dust, You can't map acceleration well, and without dust, you're left relying on gas signatures that shift too quickly to anchor predictions. Brightness made the situation worse. Reflected light depends on viewing angle. If the coma is symmetric, the brightness is stable. But if the coma is misshapen, as it was in the case of this object, the brightness changes depending on where Earth sits relative to the expanding gas. Multiple teams noticed this pattern. On nights when the comet appeared brighter than expected, it wasn't because activity surged. It was because our angle shifted. On nights when it dimmed, the same thing happened. The brightness curve didn't represent true physical changes in the object. It represented geometric changes in our perspective. And when the line between geometry and physics blurs, prediction becomes a guessing game. Then, as if to highlight the complexity further, the rate of mass loss shifted on the time scale of hours, not days, not weeks, hours. A comet shedding material at such a variable pace makes it nearly impossible to build a forward model. You can't plug an hourly change into a weekly prediction and expect the numbers to hold. Put all of this together, and the conclusion becomes clear. Every single forecasting tool astronomers normally use broke down. No rotation period, a non-uniform surface, unpredictable thermal lag, CO2 jets firing irregularly, too little dust to map the gas flow, brightness that depended more on geometry than activity, mass loss that changed too quickly for models to absorb. It wasn't one failure point, it was all of them. Nature didn't violate physics. Nature just refused to fit inside the templates we built. And this is why the title of this story holds so perfectly. The more we tracked 3i Atlas, the more data we poured into our equations, the less confident we became in our predictions. And the deeper this object moved into the solar system, the more obvious it became that none of the usual formulas were going to work. This is the moment when astronomers don't panic. They lean in. Because prediction failure isn't a defeat. It's a signal. A sign that something is happening that doesn't match the patterns we've seen before. When your predictions fail, that's when discovery begins. Avi Loeb once said. And with this object, discovery began early and refused to stop. With 3i Atlas, the collapse of prediction wasn't a catastrophe. It was an invitation, not to find fear or speculation, but to accept the limits of our understanding and follow the object wherever the data led. It's the kind of moment that reminds you why science is powerful, not because it always gets the answer, but because it knows how to keep asking questions, because it never forces the universe into a shape it doesn't fit, because nature that breaks predictions is nature at its most honest. And so the story continued. So what do we do when predictions fail? We keep watching. When 3i Atlas slipped behind the sun in late November, astronomers entered a familiar period of enforced quiet. Solar conjunction blocks our view, hiding objects behind the sun's glare and radio noise. For weeks, the comet vanished. No images, no spectra, no updates, just silence. But everyone knew what was coming. As soon as the sun moved far enough away from Atlas's line of sight, the comet would reappear. And when it did, we would enter what many researchers called the golden observation window. A brief period from December through March, when everything still left to learn about this object would need to be captured quickly before it vanished into deep space forever. That window began with a jolt of surprise. When Atlas reemerged from conjunction, it didn't look the same. Its brightness wasn't merely different, it was erratic. Some nights, it appeared sharper than expected, even a little overactive. Other nights, it dimmed so quickly that teams scrambled to verify their calibrations. The light curve refused to follow any trend line. It rose, dipped, flickered, and stabilized only long enough to change again. To astronomers, it felt as if the object was sprinting ahead of the models, daring them to keep pace. And the coma, once huge, once the size of a small planet, had begun shrinking much faster than expected. Typical comets shed their comas slowly after perihelion, a graceful retreat as sunlight weakens and activity fades. But Atlas contracted at a rate that caught even seasoned observers off guard. What had once been a vast halo, hundreds of thousands of kilometers across, now receded day by day. Instead of a slow exhale, the comet felt like a deep breath pulled suddenly inward. The shrinking coma raised the stakes. If the gas cloud collapsed too quickly, the nucleus would become harder to study. The spectroscopic signals would weaken. The chemical data would thin out. Every night of visibility mattered. And this was exactly when the chemistry started acting strange. Again, the CO2 to H2O ratio, already unusual, began to fluctuate in a way that challenged interpretation. On some nights, CO2 dominated, as it had before, perihelion, overwhelming the spectra. On others, the water signature strengthened unexpectedly, as though new fissures had opened, or deeper layers had finally warmed. And occasionally, the ratio swung so sharply that observers questioned whether the activity could really change that fast, or whether geometry was playing tricks again. The tail added another layer of complexity. Instead of forming a consistent stream, it shifted shape from day to day. The angle changed. The brightness wavered. Sometimes it elongated sharply. Other times it fanned out. Small, transient features appeared along its length, miniature kinks or ripples before smoothing out again. For an interstellar object, this variability wasn't unprecedented, but the frequency of the changes was. It was a comet that seemed to reinvent itself every 24 hours. NASA's observing teams knew the significance of this moment. JWST had scheduled time. Hubble had a follow-up slot. Even ground-based telescopes coordinated campaigns, sharing raw data across continents. The collaboration was unusually tight, unusually urgent. You could feel it in the cadence of press briefings, in the chatter of astronomy groups, in the tone of researchers online. Every day counts. This wasn't a phrase for dramatics. It was reality. Once Atlas cleared Earth's orbital region and began its outward trajectory, it would fade beyond the reach of all but the largest telescopes. By mid-spring, it would dim below reliable detection. And after that, it would be gone. Forever. Never to return. Never to give us a second chance. That knowledge created a gentle urgency, the kind that doesn't spark fear, but heightens attention. A quiet awareness that you're living through something rare, something fleeting. The sense that once this window closes, the universe will not reopen it. And that's why the post-perihelion phase became more than a scientific chase. It became a mission moment. Astronomers weren't simply gathering data. They were racing the natural fading of an object from another star system, one that was already rewriting parts of cometary science. Yet even in this critical stage, the unpredictability continued. Some observers expected the comet to fragment. It didn't. Others expected activity to spike dramatically. It didn't. Still others thought the water signature would dominate. It didn't consistently. The object followed no script. Every hypothesis had to be updated within days. Every dataset came with footnotes that began with, however, unexpectedly, or contrary to predictions. This wasn't chaos. It wasn't random. It was simply nature. An honest kind of nature. The kind that doesn't fit charts or bows to expectation. During interviews, Avi Loeb spoke plainly about this urgency. Time-sensitive data must never be delayed. And in this phase, no one disagreed. The scientific community carried a shared sense of responsibility, not to dramatize the object, not to romanticize it, but to observe it with the seriousness that a once-in-a-generation visitor deserves. Because this was the last window before fading, the final chapter of direct observation. And whether the mystery deepened or resolved, this was the moment that would define how humanity remembered 3I Atlas, not as a static object, but as a changing, living messenger from another star. And all the while, one question hovered in the air. What would Atlas show us now, after perihelion, when its shell was thinner, its activity unstable, and its true interior closer to being revealed than ever before? A comet is most vulnerable after it rounds the sun. And sometimes, in that vulnerability, it tells the truth. And what if this is only the first chapter of a much bigger cosmic story? When you step back from the day-to-day mystery of 3I Atlas, something even larger comes into focus. Something that quietly reshapes how we think about our place in the galaxy. Because the truth is, this object is not an anomaly in the cosmic sense. It is just the third one we've been lucky enough to notice. And statistically, that means there are countless others passing through all the time. We simply weren't able to see them before. For most of human history, interstellar visitors moved through our solar system like silent shadows. No one saw them. They left no traces. They came and went without a single photon reaching our eyes. Even Oumuamua, the very first one ever detected, was already leaving by the time we spotted it. 2I Borisov was brighter and easier to see, but still rare enough that astronomers thought we might wait decades before encountering another. And then came Atlas. Only a few years later. 3 objects aren't many, but in statistics, 3 is enough to reveal a pattern. Enough to say these objects aren't rare. Detection was rare. Our instruments weren't ready. Our sky surveys weren't sensitive enough. We were blind to the travelers that crossed our celestial borders. That era is ending. In Chile, at the base of the Andes, the Vera C. Rubin Observatory is preparing to switch on the most ambitious wide-field sky survey ever attempted. Its LSST, the Legacy Survey of Space and Time, will scan the entire visible sky every few nights. That means anything moving, anything brightening, anything slipping between the stars will be caught almost immediately. Astronomers expect Rubin to find between 10 and 70 interstellar visitors every single year. Not once a decade, not once every few years, every single year. The number sounds impossible until you realize how empty the night sky used to be, simply because we didn't have the right eyes to see what was passing through. And Rubin is only the beginning. Sitting deeper in the solar system, ESA's Comet Interceptor mission waits in a parking orbit, doing nothing except standing by for one moment: the detection of a new interstellar object. The instant Rubin or another observatory finds one heading inward, Interceptor will launch its probes and chase it down. Instead of watching from afar, we will fly toward it. Instead of blurry images and spectral guesses, we will get close-up data. Surface chemistry, jet geometry, direct measurements, material untouched since another star's infancy. Imagine that, a fragment of another solar system approached by spacecraft from ours. That is the era we're entering, the era of interstellar archaeology. As Avi Loeb put it, we are entering the era of interstellar archaeology. Not archaeology of civilizations, archaeology of formation, of birth, of the ingredients mixed around other suns long before our sun existed. Every interstellar object is a sample, a messenger, a piece of chemical history thrown into the galaxy millions or billions of years ago. And we are just beginning to collect them. What makes Atlas so powerful, then, is not just its own mystery. It is the fact that it represents the first chapter in a much bigger story. If interstellar objects really cross our path this frequently, then every year will bring more. Some will be quiet. Some will be dramatic. Some will carry signatures different from anything we've seen before. Some will look familiar. Others will look alien in the scientific sense, built from ingredients that formed around stars nothing like our sun. What will we discover when we can see dozens of them? What patterns will emerge? What surprises will break our models again? What stories will they bring with them? Stories written in ice and dust from worlds we will never visit. The galaxy is not empty. It has never been empty. It has always been filled with travelers. We were simply asleep to them. Rubin will wake us up. Interceptor will bring us closer. And the next decade will be filled with objects that move the same way Atlas did, silently, steadily, unpredictably, and offer us a new window into the diversity of star systems. When you understand this context, the behavior of 3I Atlas feels less like an isolated puzzle and more like a glimpse into the future. A glimpse of an astronomy where interstellar guests are not rare cosmic gifts, but routine encounters. A future where we know what normal looks like for objects born around other suns, and where we can finally see what is truly unusual. Atlas is the beginning of that shift. Its unpredictability isn't a flaw. It is a reminder that our expectations were built for a single solar system, not a galaxy. Its strange chemistry is not a warning. It is an invitation to expand the models. Its irregular jets aren't evidence of technology. They are the fingerprints of a star system foreign to ours. It is only the first chapter, and many more chapters are on the way. But tonight, one visitor still drifts quietly away. There is a quiet truth woven through every scientific mystery, a truth that rarely makes headlines but resonates deeply with anyone who has ever looked up at the night sky and felt small in the best possible way. It is the realization that if everything in the universe behaved exactly as expected, if every comet followed the rules, if every star evolved perfectly along its curve, if every question had one clear answer, then the cosmos would be a far poorer place. Predictability is useful, but unpredictability is what makes the universe worth exploring. 3I Atlas reminds you of that in a way few objects can. It isn't just a comet that broke models. It's a visitor that arrived with a simple message encoded in light and silence. You don't get to know everything. Not at once. Not completely. Not perfectly. And that is okay. You live in a world that constantly asks for certainty, forecasts, plans, deadlines, predictions. Even the language we use for science, trajectory modeling, error bars, precision, reinforces the idea that understanding means control. But astronomy has always existed in a different space, one where understanding is an ongoing conversation rather than a final answer. Interstellar objects like Atlas highlight this beautifully. They drift in from unknown star systems, shaped by forces you'll never witness, carrying chemistry that doesn't match familiar patterns. They behave in ways that resist explanation, not because they want to be mysterious, but because they are honest representatives of environments beyond your experience. In that way, uncertainty becomes something gentle, something freeing. If you knew everything, if the universe were a solved puzzle, then nights like this, listening to a quiet story under dim light, would lose their magic. There would be no wonder left, no curiosity, no reason to look up and imagine the possibilities hidden between the stars. Atlas teaches you to embrace the space between answers. It teaches you that mystery is not the opposite of knowledge. It is part of knowledge. The first step, the invitation to keep asking, keep exploring, keep listening. The astronomer's equivalent of a doorway left slightly open, leading to a room you haven't walked into yet. And that brings us to the core idea of this chapter, the line that echoes through the entire story of this interstellar visitor. Not knowing everything is not a flaw. It is an invitation to wonder, an invitation to humility, an invitation to curiosity, an invitation to slow down, an invitation to breathe. When you sit with this idea, something softens inside you. The tension of needing to understand every detail begins to loosen. The urge to control every outcome eases. You realize that the universe has been operating for billions of years without rushing toward conclusions, and it will continue doing so long after every prediction and debate fades into memory. The cosmos is not a problem to be solved. It is a presence to be witnessed. It doesn't demand that you decipher it. It asks that you listen. It doesn't require mastery. It invites connection. And in the quiet moments, like the one you're in now, that connection becomes a form of comfort. There's something profoundly peaceful about acknowledging that not every answer arrives when you want it. Sometimes you wait. Sometimes you watch. Sometimes you accept that you're part of a story much larger than your own. A story written across light years and centuries, and the slow drift of ancient ice. Even astronomers experience this comfort, though their work is built on measurement and precision. When models fail, they don't see the end of understanding. They see the beginning of discovery. They see the horizon widening. They see the chance to learn something new. And you can carry that mindset with you too. The unpredictability of 3i Atlas becomes a reflection of life itself. You can plan. You can chart your path. But some things will always surprise you. And those surprises, those gentle disruptions, are often the moments that pull you into greater awareness, deeper reflection, or unexpected joy. In that sense, Atlas is more than a comet. It's a mirror, a reminder that you don't have to have everything figured out. that you don't need perfect certainty to feel safe, that the unknown can be a companion, not a threat, that the path forward can be illuminated step by step, not all at once. As you let these thoughts settle, you may notice your breathing slowing, your shoulders softening, your mind easing into a quieter rhythm. This is the gift of cosmic philosophy, not to overwhelm you with abstractions, but to gently guide you toward stillness, toward rest, toward the understanding that some mysteries aren't meant to keep you awake. They're meant to lull you into calm. In a universe this vast, knowing everything is impossible, but feeling at peace within that vastness, that is entirely within reach. And so, the traveler begins to fade. By now, the interstellar visitor that once startled telescopes and challenged every model we held is drifting into a gentler chapter of its journey. The sharp intensity of its perihelion days has passed. The rush of activity, the brightness spikes, the debates, the measurements, all of it now falls behind like echoes settling into distance. As weeks unfold, 3i Atlas moves steadily outward, gliding into a region where sunlight thins, where warmth fades, and where only the quiet remains. This is the part of the story where the universe exhales, and you along with it. Far from the sun, the comet's once expansive coma softens. What was once a vast cloud of illuminated gas begins to collapse gracefully inward as the heat that once drove its activity fades away. It doesn't happen suddenly. There is no dramatic flicker, no final burst. Instead, the coma dissolves slowly, almost imperceptibly, like breath, vanishing from a cold morning. Each night, astronomers take one last set of images, and each night the glow shrinks just a little more. Its colors fade too. The bright greens and soft yellows that once signaled ice turning to gas now dim into neutral tones. The light becomes muted, softer, a whisper instead of a voice. And as the color drains, the object becomes somehow more beautiful, not as a spectacle, but as a memory. A guest who came from far away, stayed briefly, taught us something, and then continued on its way. You can almost picture it. A quiet traveler, slipping through the dark, a dim ember drifting toward the edge of sight, a whisper leaving the room just as you begin to fall asleep. There is no urgency now, no need to interpret jet structures or track rotation, no need to wonder about predictions or anomalies. This chapter is not about solving anything. It is about witnessing, simply witnessing, letting the moment be complete without demanding certainty. Because some cosmic stories end not with revelation, but with resonance. As Atlas fades, its tail thins into a delicate thread, so fine that only long exposure cameras can see it. The dust, once sparse but still present, drifts behind in a ghost-like trail. Sunlight barely touches it now. The faint glow feels like a distant lantern slowly being carried away by an unseen tide. Eventually, even that thread will disappear, and the comet will return to what it has been for billions of years. A solitary traveler wandering between stars, untouched by observation, unburdened by explanation, just drifting, quietly, patiently, holding its secrets until another civilization, perhaps in another time, happens to see it pass. There is comfort in this image, more comfort than answers could ever bring. Because as you watch Atlas diminish, you begin to understand something soft and reassuring. You do not need to solve everything tonight. Not this comet, not this day. not the questions that linger in your mind. The universe isn't asking that of you. The world will still be here when you wake. The problems waiting on your desk will wait a little longer. The inbox can remain unopened. The uncertainties can rest where they are. You can let them drift for now, the same way Atlas drifts away from us. In the hush of this moment, your breathing slows without effort. Your shoulders loosen. Your thoughts settle into a calmer rhythm. The story has carried you this far, and now it gently lets you rest. The comet becomes a lullaby in motion, a reminder that movement can be peaceful, that endings can be soft, that mysteries can close like a book laid quietly on the nightstand. If you could see Atlas now, you would not see drama. You would see serenity, a dim point of light moving through infinite darkness, a presence that no longer asks to be understood, only acknowledged. And in this softness, a small farewell rises, simple, quiet, and complete. Good night, traveler. A whisper for something that never belonged to us, but passed close enough for us to feel its presence. Close enough to remind us that we are part of a universe that breathes, moves, shifts, and invites wonder at every scale. As the comet continues outward, the noise of the day begins to fade as well. The momentum of the world slows. The mental clutter dissolves. The edges of thought blur the same way the coma blurred before vanishing into night. And you find yourself sinking gently into the quiet, carried by the rhythm of distance, the calm of retreat, and the knowledge that some journeys are beautiful precisely because they are brief. And as the comet fades, so does the noise of the day. As the last traces of Three-Eye Atlas retreat into the darkness, the story it carried begins to settle gently around you. What started as a discovery, a streak of light spotted from a telescope in Chile, became confusion as the data challenged every familiar pattern. That confusion opened into mystery, a mystery that widened with every new observation, every strange spectrum, every unexpected turn. And in the end, the mystery softened into acceptance, into the quiet understanding that not everything asks to be solved. Some things simply ask to be witnessed. You followed the traveler from its first faint detection to its brightest moments near the sun. Through the debates, the surprises, the shifting science, you've seen how its behavior refused prediction, how it broke models, how it invited questions far bigger than itself. And now, as it drifts outward into the dark, the noise of the journey fades and leaves behind a quiet truth. The universe is vast, unpredictable, and full of wonders. But you are here, in a small, safe corner of that vastness. No matter how big the cosmos becomes, no matter how far these visitors travel, your space remains steady. The ground beneath you is solid. The air around you is calm. The night outside your window might stretch into infinity, but it is gentle tonight. It is soft. It is steady. And nothing in its depth is reaching for you or asking anything of you. The stars are not loud. The planets are not hurried. The universe is not roaring with chaos. It is breathing, slowly, steadily, peacefully. And as you listen to that rhythm, perhaps you feel your own breathing begin to match it. Inhale, exhale. A little slower than before. A little deeper, a little softer. The same way Atlas dimmed gradually, naturally, without tension or urgency, you can let your thoughts dim too. You can allow the day's weight to loosen its grip. You can allow the unanswered questions in your life to rest untouched for now. The cosmos does not demand solutions tonight. It offers stillness. You might picture Atlas, now only a faint point against the darkness, gliding toward the outer reaches of the solar system. There is no sound in that motion, no pressure, no rush. It simply moves on its path, following currents of gravity and light that have shaped its journey for millions, maybe billions of years. Watching it fade reminds you that life does not need to be solved all at once. Sometimes it just needs to be lived, one quiet moment at a time. Tonight, you are allowed to rest in that quiet. The world around you may have challenges waiting, tasks, responsibilities, expectations, but not right now. Right now, you are wrapped in the softness of a story that has carried you from curiosity into calm. A story that stretched wide and far, but returned you gently to yourself. Discovery became confusion. Confusion became mystery. Mystery became acceptance. Acceptance becomes rest. And here, at the end of this journey, the universe feels close. Not as a vast frontier, but as a quiet companion. The same dark that cradles the stars also cradles you. The same silence that surrounds Atlas surrounds you too. You are not lost in the cosmos. You are part of it. And within that connection, there is safety. Let that feeling settle. Let it deepen. Let it pull you softly toward rest. There's no more story to follow tonight. No more questions to hold. No more thoughts to chase. Just the quiet. The deep, gentle quiet of a universe that is not asking you to understand it, only to rest beneath it. A universe that turns slowly, breathes steadily, and offers peace in its vastness. And so, as you lie here, with your breath softening and your thoughts fading like Atlas drifting into the dark, let the final words of this journey settle into you. Let them echo lightly, like a whisper meant only for this moment. You are safe. The universe is quiet tonight. No transition, just rest.